All right, today we are going to start section 4.1, which is antiderivatives. And just before we go too far into what that actually looks like, I just want to do a real quick refresher, a remembrance of what derivatives look like. So you have a list, all the front page of this set of notes, okay? And I'd like for you to go down and to write in what you remember as your derivative for each one of them. If you make a mistake, it's okay. We're going to make sure everybody has them all written in correctly. Not incorrectly, but written in correctly. So just go ahead and fill those in. So the constant rule, linear function rule, constant multiplier rule, sum and difference, power rule, and then my next slide has all the trig rules on there as well. So jot those down for me. And we'll take just a couple of minutes to fill those in. Let's fill in some of these together. If you're not quite done, that's all right. What is the constant rule? What is the derivative of a constant? Yeah, it's just 0, right? So the derivative of a constant is 0, no matter how that constant looks. So if you'll remember on your gateway, sometimes those constants looked maybe not like a whole number, right? It might have looked like e to a 5, right? That's a number. Or the natural log of 7, that's a number. What about the linear function rule? This almost feels funny to call it a rule, but we do use linear functions frequently, so we've got a separate statement about it. What's the derivative of ax plus b? Yeah, just a. And if you remember, the whole point is that derivatives are slope, and so that one, the slope's constant because it's a line. What about when you have a constant in front? So you've got a function, but it's multiplied by some number, k. What happens to the k? It's just k. I use the phrase, it comes along for the ride, right? It doesn't change. It doesn't really affect anything. It's just part of the derivative then. But we take the derivative of the other piece that is a function in terms of x and multiply that by k. Whether that's a power rule or whatever it is, that's how we deal with it. How about f of x plus or minus g of x? What happens on those when there is a sum or a difference? Yeah, you just take the derivative of each piece and you add or subtract, whichever way it was, them together. Let me shift that back over some. Okay. And how about the power rule? What's the derivative of x to the n? To the n minus 1, right? Let me just decrease the power by 1. And again, the power doesn't have to be a whole number. It could be a decimal or a fraction, or it could look really weird. It could be a square root or something. It would still be okay and would follow still follow the same process. Your trig rules, probably your favorite ones. Definitely I don't know, I feel like they're the hardest to remember compared to the ones before. They just aren't as frequently used, so they're harder for me to remember. What's the derivative of sine of x? Yep, cosine of x. And what is the derivative of the cosine of x? Negative sine x. And I'm pretty good on those two. And then after that, I have to start thinking harder because those two just go back and forth between each other. Does anybody remember the derivative of tangent? Secant squared x. Good job. And then, so what's the derivative of secant? Not secant squared, but secant. Yeah, secant tangent or tangent secant would be fine, yeah. Secant x, tangent x. How about the derivative of cotangent? Good, it is negative, and it's cosecant squared. I kind of, if you'll remember, kind of talk about the fact that every time you have a co, there's 3 of them here, I haven't got to the last one, they all have a derivative that's negative. Their signs always change for the derivative of the co-functions. So in fact, this happens down here as well. I have a negative, and then what's the derivative of cosecant after the negative? Cosecant x, cotangent x. And there's some of these that sort of seem like they're operating in tandem, like they're pairs, right? These two seem awfully similar, and these two seem awfully similar, right? Those grayish ones, those pinkish ones, they've got the same kind of pattern going on. Okay, so these are all derivatives. And the reason I bring them up is not because you don't know them, because you do know them, but it's to remind you of the fact that as we move into the next section of material, which is antiderivatives, what we're really doing is we're really starting on this side and we're trying to go backwards. Okay? So we're starting again on this side with something that's already is a derivative, basically, and we're going backward to the original function. So a lot of our rules are really just operating in reverse. So let's take a look at what that looks like. So the first one is the 0 rule. So what would I have had to take a derivative of to get a derivative that is 0? What would have had to look like to start with?
X.
Not x, but you're close. Just a constant, right? So notationally, I need to give you some notation. When we do antiderivatives, like this is actually starting as y, what we do is we capitalize it. So you're going to look at like a capital. So if it's little f of x, it'll be a capital F of x and so forth. So I'm going to use capital Y's. So this is some constant, c. You can use a c or a k for constants, doesn't matter to me. But you're getting a constant, right? Because you're going backwards. And this is essentially this same rule right here, going back this way. I'm starting with 0, and I'm going backwards to getting a constant. What then do I get if I have a constant as my derivative? What would that have been in order for that to have happened? A constant times x. We'll get there in just a second, but you're right, Emma, yeah. Okay, so start out, and I said, there's my x. Too many things going on at once in my head. A constant times x. So if I took the derivative of kx, it would just be k, correct? K is a number. Whatever the number is in front, the derivative of kx is k. But there's a catch, and the catch is that I could also have a constant on the end of this, because when I take the derivative of a constant, I get 0 and it disappears. So what you're going to see happen on every single one of these rules from here forward is they're all going to say plus c at the end, because there's always the possibility that that happened. And also, if you think about what we're doing, we're talking about the shape of a curve. Right? That's what the derivative tells us. The derivative tells us something about shape. It doesn't tell us where actually the curve is located. So if the shape of a curve is shifted up or down from where it was, I lose that information when I take the derivative. So there's the ability, when I put the plus c back in, to get that shifting up and down to actually show where the function began on a graph. All right, so what do you think happens when I have a constant multiplier times the function? What happened when I had a derivative?
K is constant and f of f prime.
Yeah, I did k is constant. It doesn't change, and it won't change here either. The k will stay constant. And when I took derivatives, I just took the derivative of the other piece. So when I'm taking antiderivatives, I'm just going to take the antiderivative of that other piece. So there's that capital F of x I mentioned earlier. Lowercase f to start, capital F of x when I'm going backwards. And again, plus c on the end. What do you suppose is going to happen when I have sums and differences? Yeah, it's going to do the same, right? I'm going to end up with these capitals, capital F of x, the plus or minus stays there, and capital G of x, and then plus c. All right, here's the most interesting one that we've had so far, x to the n. So let's think for a minute about what we do over here when we take a derivative. When we take a derivative, we take that power that's there and we bring it down as a multiplication factor, right? So what would be the opposite of multiplication? Division. We're going to see division happening here, right? Like, I'm not trying to trick you. These are leading questions. These are the kinds of questions you're not supposed to ask, but we're doing it anyway. Leading questions. So yeah, I'm going to get division. Also, I use my current power when I'm working with derivatives. I take the current power down, right? And so I'm multiplying by it. Well, I'm actually going to, and then I decrease my power by 1. Yes? Okay. So instead of decreasing the power by 1, what do you suppose I might do? Increase the power by 1. And instead of using the current exponent in the problem, I'm going to use the new exponent that I've achieved. So let me show you what this ends up looking like. We increase the power by 1, and we divide by the new power. Let me put my plus c on the end, and let me just do a real quick example so you can see that it really works. It's not just magic. It's math. It's math, not magic. Okay, so let's take a look. So let's see what would happen if I had x, we'll do x to the 5. So according to this rule, what I should have is I should have a capital Y. It should be x to the 6th over 6th, right? Okay, now take the derivative of that. If I took the derivative of x to the 6th over 6, the 6 would come down in front, which would then cancel with the 6 in the denominator, and I'd decrease my power by 1 to be a power 5, and sure enough, I'd be back at y to the 5th. Are you with me? Of course, there's a plus c on the end of this one. That's not my point at the moment. I wanted to show you the x to the n part working out. Does that make sense? Okay, so I increase the power by 1, and I divide by my new power. What you will notice is these are not your trig functions. They really are all those derivatives on the right-hand side showing up again with maybe not a negative involved, but that's what you're really seeing. Okay? We will get to the other part of the trig functions antiderivatives later, but that's not right now. Okay? So we'll get there. Right now we're just working in reverse. So if I had if I had the function, the derivative of sine of x, what would that have come from? How would I have gotten that to be my derivative? Yeah, it'd be a cosine, and it would have to be negative, because the derivative of cosine is negative sine, right? And of course, I have plus c. What would I have had to take the derivative of to get cosine? Sine. Again with a plus c. Whose derivative is secant squared? Tangent plus c. Whose derivative is secant tangent? Secant plus c. Whose derivative is a cosecant squared? Yeah, it's cotangent, but again, I got a negative going on, right? Because there is actually not a negative over here, right? You don't have one in the form that you're starting with, so it needs to be in the other piece. And then the last one, what is the whose derivative is cosecant cotangent? Negative cosecant x. All right. I'm going to double check on my timing on this when this happens. Next Thursday, not 2 days from now, but 9 days from now, you guys are going to do for me your second gateway. And it's this. Okay, we'll have a few other rules before we get there. Which that's what I was wanting to check on, is where this falls, because I couldn't remember. But this is going to form the basic premise of what we're doing. What you won't see is you won't see product rules and quotient rules and chain rules because it's not quite so straightforward to deal with them in reverse. They're very complicated. We will see just a touch of how to deal with a small percentage of issues like that in our very last section of this chapter. But the rest of the how do we deal with things that look like products or quotients or whatever is actually an entire chapter of Calc 2. It's chapter 5 in your book. And it isn't even all-encompassing, even at that. There are actually tables in the back of your book that you have to use sometimes because there's just not a closed, clean way of doing it. That's how messy those are. So everybody says, thank you, because that means that these actually are not as complicated as derivatives. That's what it really means, okay? So we're going to do some examples of these and play with them a little bit, going with antiderivatives. When you do the gateway, and we'll remind you when we get there, the biggest thing people forget, maybe not the biggest, but I had somebody do it, I've had more than one person do it, where they don't put the plus C's on anything. And you guys know that on a gateway question, if you don't have the plus C, what's going to happen? It's wrong. I had a student get everything completely correct except for plus C was missing on every problem. It's been a few years back that happened, but it will, it can, it doesn't have to, but it can happen. So remember your plus C's as we're working. Okay, so I haven't really talked about this notation, so let me introduce you to this notation. This script S at the beginning and this dx at the end are kind of like a beginning and an ending parenthesis, okay? Kind of like that. So anytime you have the script x, you're going to have the dx. They go together. They start and they end what you're doing. And their notation actually says, find the antiderivative. That's what it is. That notation means find the antiderivative. So the script s at the beginning kind of gives you that clue. The dx at the end is telling you what the variable is. And I know that for what we're doing right now, it's like, well, duh, the variable's x. There's no other variable in the problem. But the reality is that that's a limited true statement. Calc 3, again, I know not many of you probably are planning to go through that far, although it's a super fun course. I love teaching Calc 3. We do what's called multivariable calculus in Calc 3 and Calc 4. And you have multiple variables within a problem, so you need to know what the variable is that you're considering at the moment. So that's the notation there, and that's why it's there. Okay, so ours are all going to have script x and script s and then the dx at the end to begin and end our notation. All right, so what we're going to deal with is we're going to deal with these. When I write the next step, you'll notice they go away. It's kind of like limits, right? Once you actually put the value in, there's no more limit notation at the beginning, right? Once I actually take the antiderivative of whatever pieces I have, I don't need the notation that says find the antiderivative because I've done it. So I won't be rewriting that step because I won't need it. All right, so if I have 2x, there's a couple things that you could do. You could flat out go back to your list of rules and very strictly follow them. Or you could also ask yourself the question, especially in some cases, what would have given me that derivative? And on this one, you can do that pretty well. What would have given you a derivative of 2x? X squared. And if you aren't sure, maybe it didn't say 2x, it says 5x, and you're like, okay, what do I do? The actual process is that right now the x has a power of 1, correct? So we would increase the power by 1, that's x squared, and we would divide by that new power 2. And if you see, that 2 would cancel out with the 2 that's in front. So that's what would be physically happening if you went through it the long way. Do you know what would have given you a derivative of 3x squared? Yeah, x to the third. Good job. And again, you can do the same thing. If you didn't see it exactly as you expected it, You increase the power by 1, that makes it x cubed. And then you divide by your new power 3, and the 3 would cancel with the 3 at the beginning. Am I done? What's missing? Plus c. Now I'm done. Okay, so let's get to some that are a little bit less direct. Number 2. So this is an example of one where, I'm sorry, yes ma'am?
On the gateway, do you want it the long way or the short way?
I don't care. It doesn't matter to me at all. Yep. And you don't have to simplify, so if you do it the long way, you don't have to cancel the 2's out or the 3's out either. Yeah. Okay, so on number 2, you'll notice that it looks like we have a denominator, and just a minute ago I told you you don't have to do the quotient rule, like there's none of that going on. So I need to change what I'm looking at. Tell me how to change it, Connor. Right, so I'm just going to do one step to rewrite. So this will actually say x to the negative 6 minus 2. Notice when I rewrite, the script s is at the beginning, the dx is at the end, telling you that I'm not done. I didn't do any calculus. All I did was a little bit of algebra rewriting. But now I can use the rules that we've been working with and just learned. What would I do with x to the negative 6? I'd add 1 to negative 6. So what is negative 6 plus 1? Negative 5. And I would divide by my new power, negative 5. What about the negative 2? Like this minus 2 at the end. Yeah, it would be negative 2x. Remember, anytime there's a constant, I will now attach an x to it. Okay? And then I need plus c. So on a gateway, since you had asked Lexi, on a gateway we would stop here. We wouldn't do anything any further. As you're working on your homework and as you're putting things into cleaned up notation, your answers should look like the question began. So this question did not start with negative exponents, right? So the answer at the end shouldn't have negative exponents either. So as I finish this question up, I would do just one little bit of rewriting, cleaning up, that would look like, you can put the negative in front if you want, I don't care where the negative is, but it would look like 1 over negative 1 over 5x to the 5th minus 2x plus c. And that would be our final answer for what we're working on as far as homework and regular exams and so forth. Any questions on that one?
On the derivative test, can we leave the exponents negative?
Absolutely. Yeah, this is totally a legit way to stop on your gateways, because gateways require no simplification. All right. So again, we're looking at pieces that don't quite look like my rules, and I've got to change them so that they do. So any ideas about how to rewrite this so that it would look like one of the rules that I now have? Okay, so let me do that part of it first, like you just said. Change this so that it says x and x to the 1/2. Okay, that's a great first step. What else would I need to do? Yep, what would that exponent be, Damon? Do you know?
3 over 2.
Yep. So I can combine my exponents, add them together, and I get 3/2. And I need one more step.
Then you can just bring it up and make it negative.
Okay, and Damien did a really good job of walking us through all the pieces of that. If you can move through them without having to show the steps, that's totally fine. But those are all the pieces of how to combine those together and to move them into the numerator. And now it actually looks like one of our new power rule, right? So what do I do with my new power rule? What does it say I do? What will I do to the negative 3/2 as a power? Yeah, I add 1. So, go ahead, Eric. I'm sorry.
Plus 1 and then divide with the new problem.
Right. Okay, so some of you get a little nervous working with fractions, especially on my gateway, when I'm telling you that I'm going to take things off if you mess them up, right? So if you left it like this on the gateway, it would be okay. We're not going to leave it like this right now, but it would be all right in that context. What is negative 3/2 plus 1? Yeah, negative 1/2. So let me clean up some stuff. So this is x to the negative 1/2. I got my plus c, good. And then I've got negative 1/2 in the denominator. So there are several things that still make this not a good way to end my problem. Can somebody give me one thing? One thing about this that is less than appealing. There's a negative exponent. What else?
1/2 can be written as just 2 over 1. Negative, or just 2. Negative 2, but 2 on top.
Okay, so the fact that there's a fraction in the denominator, does that sound right, Emma?
Yeah.
Yeah, fractions within a part of our function, like in a denominator and a numerator, yeah, that's not cool. Okay, there's one more thing. So let me fix those two, and then we'll identify what the last thing is. Actually, it might help. So Emma mentioned that I could actually, instead of dividing by negative 1/2, I could multiply by 2. And she's right. And I'll just go ahead and multiply it by negative 2 for the moment, just so that I can move the negative at the same time. So if you multiply the top and bottom by negative 2, you can see how this will cancel out, right? So you actually end up with negative 2. And you had also mentioned that we don't want to have the x to the 1/2 as a negative, so then we will x to the 1/2 in the denominator, and then plus c. There's still one more thing, though, that's not ideal. Yeah, and it's not that there's anything wrong with powers of 1/2. There isn't. It's just that the problem started with a square root, right? It didn't start with exponents that had fractional quantities. So we are going to rewrite it as that value when we're done. So this is negative 2 over square root of x plus c. And I know that in trig, you get concerned when you have square roots and denominators. But please remember in trig, when that happened, it was always square roots of numbers, not square roots of variables. So square roots of variables are not an issue, because it depends on what the variable value is as to whether this is a rational quantity or not. So this is a perfectly acceptable solution to my problem. Any questions on that one? All right, 4. What does it look like is happening on 4 that's maybe not quite so cool? What is it? Here's multiplication. It looks like there's somehow like a product rule thing going on, right? But I just told you a few minutes ago that we're not doing any product rules and quotient rules. So we would need to multiply it out, right? So if it looks like there's multiplication, you've got to change it so it doesn't. If it looks like there's a denominator, you have to change it so that there's not. And so that's exactly what we're going to do here. We're going to distribute, multiply, whatever word you want to use. We're going to clean this up. So I have x times 3x. That's 3x squared. Let's see, I have minus 2x plus 3x, and then minus 2. And you could go from here if you wish. I am going to clean up my 2 middle terms just because they can be simplified. And then I have minus 2 dx at the end. Okay, does that look all right? All right, now that it's in that form, I can use all the rules that I've been using. This doesn't look that much different from some of the others we've already done. So let me just kind of write it out the way that you might think of it, since we've started seeing values that don't always work this way. You would increase your power by 1 and divide by your new power. X, well, that's x to the 1, right? So I increase the power by 1, makes it x squared, and divide by my new power. And then I have a 2, so that would be now 2x and plus c. And then the only cleanup step you might not even have, because you might not have done what I did, is to recognize that the 3's do in fact reduce. So this could be written as x cubed plus x squared over 2 plus 2x plus c. I think it was minus 2x, wasn't it? Yeah. Okay, any questions on that? Is your going to have to use some algebra on some of these to simplify before you keep moving forward. No lesson would be complete without some trig involved, right? So we're going to do a couple of trig examples. There's still two pieces of this, right? I have this piece and I have this piece, so I'm going to treat them just like the sum and difference rules that we've done on the other problems. What's the antiderivative of 1? It's just x. And then what's the antiderivative of negative cosecant x cotangent x? Is it negative or is it positive?
It's going to turn into a positive.
Yeah. Yeah, so there's a negative already there, and then the part that I underlined in red would be negative cosecant, which is what Maurice is saying, right? And then I would have plus c. If you already jumped the gun and recognized, hey, look, there's the negative I needed there anyway, and you jumped to the end of this piece right here, that's totally fine. So I would have x plus cosecant x plus c. All right. What weird things are going on number 6? You're going to have to simplify something because this is a quotient, right? And there's no quotient rules. I mean, there will never be a quotient rule for an antiderivative. You're just not going to get one. So I got to simplify this some way. I posted back when we were doing derivatives some trig identities that might be helpful. So if you haven't already printed those off, or if you want to just access them online, that might be a good place for you. This would probably be a good place for you to do that. And you could end up with some simplification of a little bit of trig, not extensive, crazy simplification, but a little bit, even on your gateway. All right, so just expect that that might be the case. Any ideas of how you might simplify anything you see on this particular trig problem? Yeah, the denominator does equal cosine. That is actually called a Pythagorean identity. So this is sine x on top. The denominator is actually cosine squared of x. Okay, everybody good so far? All right, now it still looks like division though, yeah? So any other thoughts about what you might try to do next? Because sometimes it's really just, we just try something and we see if it works, and if it doesn't, we erase it and we try something else, right? So what do you think, Eric? What'd you say? Okay, so why did you, I mean, you've got part of what you've said right. Can you tell me what you're thinking when you're trying to do what you're doing?
Well, you have a sine x and you have a cosine squared x, so you're going to be left with one cosine.
Okay, so I think that you're telling me that I could separate my cosines like that. So if I separated it out, there's another cosine over here, then I'd have sine over cosine, which is tangent, right? And then I'd have this other piece, which isn't cosine, but it's 1 over cosine, right? Okay, this is a good thing to do. It's a good try because it allows us to manipulate something into something that doesn't look like a fraction. Sine over cosine is, in fact, tangent, and that's useful. How else can I write 1 over cosine then? That's secant x. And now I can deal with it because I have an antiderivative form for tangent secant. What's it look like?
Secant x plus c.
Yep, secant x and plus c. That's exactly right. So the hard part about that problem is not the calculus. The hard part is identifying which trig functions are going to be useful and applying them in the right way. All right, so I've mentioned you're always going to have plus c's, and that's true when you're finding general antiderivatives. And if you go back to the very beginning of these problems, well, even on each slide I did it, it says we're finding the general antiderivative. But sometimes we can actually find out what the c value is. Maybe it's 0, maybe it doesn't really exist, so to speak, or maybe it's some other number. And so that's what we're going to end with today, is to find a particular solution. So the other ones were general solutions. They've got the plus c because what we're saying is they could shift up and down from there. It doesn't change the shape, it just changes the location, and I'd still have the same derivative. But we're actually dealing with these problems where I'm given a initial condition. I'm told something about the original function. So the beginning of the problem starts out exactly the same, and I'm going to have the plus c and all that jazz. I'm just going to end with using this information that I wasn't provided with before. So ignore the part for the moment that's boxed in, because it's not necessary until the end. What is necessary is to take this equation and to find the antiderivative. Now notice, this starts out telling you that the name of this equation is f prime. So when I find the antiderivative, it won't be capital anything. I don't have to worry about my script s. I'm just working backwards, and so I'm going to use f, because this says f prime, and to go backwards means I would go to f. So I'm starting with f of x. And I need the antiderivative of 4x squared. So what am I going to do? Not to the fourth, to the third. And then put 3 in the bottom, and then plus c, thank you. Okay, this is the general antiderivative. It just is. And then we're going to use the part that's boxed in, the initial condition, to find and solve for c. So as I'm moving on from here, I'm going to actually find f of -1. So that actually means 4 times -1 cubed over 3 plus c. And what I know is that that is actually equal to 3. So this is now what I'm going to solve to figure out what c would actually have to be to make that work. So, what's -1 cubed? -1. So this is -4/3 plus c equals 3. Let me erase that one. So I would add 4/3, right? What is 3 plus 4/3? 13/3. That's right, because 3 would be 9/3. 9 plus 4 is 13. Is 13/3. So my solution to this initial value problem is that f, I wrote down prime, I didn't mean to. F of x is equal to 4x cubed over 3 plus 13 over 3. There's no plus c because I found it. Okay, so graphically, visually, what did I do? Well, I told you that the plus c has the ability to take whatever the shape is and just shift it up and down. It's a translation, right? So what has happened is that you've lost that ability because somebody said, but this point is on your graph. And so now you're fixed. You can't shift it up and down anymore because it has to go through that particular point on the xy plane. Okay, the next problem is a little bit trickier because they don't just give you f prime and you ask to find it, an initial condition. They actually give you f double prime as well. So let's take a look at what's happening on this one. If I'm starting with f double prime, I should be able to take this and go backwards one step and find f prime, right? It's just the antiderivative. So what is the antiderivative of x squared? Yep, x cubed over 3 plus c. And I'm told an initial condition. Ooh, that's really big, bold. I didn't mean that. How about we use this one? I'm told an initial condition about the derivative. I'm told that the derivative at 0 is equal to 8. So I can use this information just like I did on the previous problem. So this tells me I can find f prime. Actually, let me write it over here since it's the way I did before. F prime of 0, which is 0 cubed over 3 plus c is equal to 8, which means what's c? It's 8. So what I know is I know that the derivative is x cubed plus 3. I'm sorry, x cubed over 3 plus 8. What I'm not done, I'm supposed to find f. But can't I just do it again? Just recreating the same process I just did. And so now I'm going to find f of x. So what is the antiderivative of x cubed over 3? Okay, so x to the 4th, right? Increase the power. The denominator, which previously had a 3 in it, now has a 4 in it as well, because I'm dividing by my new power of 4. So that makes it 12 in the denominator. Plus what? Plus 8x plus c. And now I'm going to use this information with this initial condition to figure out what c is in the second problem. Now, it probably would be a good idea, just so that we're not confusing the issue, to recognize that these are not the same c values. So the first one is c1, and the second one is c2, right? They're not the same. They're just arbitrary, but they're not supposed to be the same thing. So I took this information and I found f of 0 now. I'd have 0 to the 4th over 12 plus 8 times 0 plus c equals, what is it, 4? What's c? 4. It's really nice because these are polynomials, and that doesn't always happen, but it is kind of nice. This is c2 is what I called it. c2 is 4. So my function, f of x, is x to the 4th over 12 plus 8x plus 4. And any idea how you could confirm that you did it right? Any guesses? What could you do to make sure you got the right answer? Take the derivative, check that it actually made sense with the initial condition for the derivative, and then take second derivative. And you'd actually should, if you did it right, be back at f double prime of x equals x squared. So you can confirm by going through the process you already know with derivatives that you've achieved or arrived at the correct antiderivative. Any questions on those? Okay, so we're done early today. Go have a good lunch or whatever, and I will see you guys on Thursday. We will be continuing along this process of antiderivatives.